Um, so thank you all for coming for this session. I'm very excited to share our, the development of this technology based on deep reinforcement learning to do the power saving for fan control. Um, so I'm the only presenter today. My two other co-presenters are unable to make it today. So does it make it to the, yeah, my arrow? Okay. Yeah, maybe that presentation. Right over there.
Just the right one.
It is on right.
Try the clicker.
Yeah.
Not really sure.
Should I start over again?
Yeah, you can press escape and try. Anyone want to try to provide PowerPoint support? It's advancing on his screen, but not.
Maybe it's just slow.
All right. Very good. Thank you. Appreciate that. So a little bit of background about me and the company and the product. So I'm a principal engineer at Axiado. I specialize in security, but I do lead other projects such as the dynamic thermal management, this project. Before joining Axiado, I worked for Intel for 23 years. Axiado is a Bay Area-based, San Jose-based company. We are 100 plus employees in total, and we are in 4 different geos. So the heart of all the products that we develop is a chip that we designed called Trusted Compute Unit. It basically has these 4 components. Application processor that has cores to run BMC and also to run the vulnerability management products, the XDR applications to detect ransomware or for firmware security. And then we have the programmable AI engine. It's basically an accelerator, machine learning accelerator. And then we have SmartNIC. That's basically to manage the security of the control plane traffic, such as BMC with network as well as web application firewalls in it. And then the last piece is the hardware root of trust, and then the TPM to store your secrets and do other security necessities. So we offer different kinds of cards. The card that is of relevance here is the DCSM card, DC Secure Control Module, and that's a card we use to connect to the server to manage the fan speed. So just want to give a quick background of how we conceived this project, how we chose DRL. Roughly 8 months ago, our CEO said, there is a customer demand for power saving. What can we do using our machine learning to optimize the power, yet not to compromise on whatever benefits people get from today's fan control, either using PID controller or static fan speed, whichever one they use. So we as engineers, we thought about 2 questions for us. One is DCSM the right product to manage the fan control speed? And then the second one is, what is the right machine learning model that we should choose? For the first one, is DCSCM is the right product? So I'll highlight 3 or 4 items. Because it's a, because it's a DCSCM, we run BMC on it. And as you all know, BMC is used for management of different things on the server, including power control. So it's a natural fit for us. So there is no question there. And then the second part is, using the BMC interfaces such as OpenBMC or Redfish, you can get the thermal sensor data, voltage, and current fan speed, so on and so forth. However, we also wondered if we are going to introduce machine learning, if we have a richer data set, how would we get it, and how we would make use of it. So this part is very easy because it's a BMC. We have a lot of different connectivities, I2C, SPI, and whatnot, right? And then we gather a whole lot of data about the chassis in general, right? So it's a great fit there. And then we have like I mentioned, the chip has the ML engine, the ML accelerator. So we won't have any problem with that aspect of it. And then the last piece is the hardware-based security. Like I mentioned, since BMC is security sensitive, even though it's not a security application, it's security sensitive. Because if your BMC or your controllers don't run, or if they are attacked, you are going through a denial of service attack, your server could go down, right? So security is important, it's relevant, and then we offer that. So that's how we thought, okay, we are solving the right problem, and we are the right party to solve it. And then moving on to the second part, what is the right machine learning algorithm to choose, right? When we submitted this presentation, we shared 3 links, I'll just flash it to you guys, where DRL is used successfully for thermal management for different scenarios, like you guys can read this article from Google, where they used AI in general to do the cooling and power saving. And then there are a couple of other articles, here, the dynamic thermal management, where somebody has successfully used DRL to control the fan speed. And then the AlphaGo, this you all might be very familiar with. So very complex application was learned by DRL very quickly without any human expertise, and then it could start beating the humans. The last piece I forgot to include it in the presentation, but I just added it here. So at a high level, there was a paper on Nature published by some leading authors in DRL. They worked with the Swiss lab, the research lab, where they basically, the lab has a very complex control system to basically position and control the shape of a plasma, right? And you see on the right, sorry, on the left here, they had basically they have 18 coils, heating up that chamber, and each coil is controlled by a PID controller, and the experts have calibrated it over the years. And then these guys came along, and then they worked with them, and on the right, I kind of summarized what they said. In a very quick time span, they could create a system that could easily be in the future, replace the existing control system. And also it simplified the overall architecture of the control system, right? So feel free to check it out. So now going back to the power saving conversation. So as you see in the table, the TCU, DTM, ML, DTM stands for Dynamic Thermal Management, ML is for Machine Learning. So we compared it against a static fan speed, like 2 different fan speeds, at the cycle of 65% and against 80%. And you see these numbers. Essentially, we ran this on different servers. This is kind of an average. As you might know, fans could consume 20% of the server's power. And then yesterday I was listening to a presentation. They were saying that it could, in a data center, it could be up to 35%. So we have put the conservative numbers, assume that you save 10% of the energy. And we are looking at annual savings per server is $70. And then you could save up to $7 million a year for 100K servers, right? This is a conservative estimate here. So in terms of how we did it at a high level, we are basically pulling data from different sensors every 5 seconds. We've been doing it for 6 months. And we trained on random workloads without knowing much knowledge about the workload, but at the same time, pretty intense, right? Different database operations, AML operations, and whatnot, right? That's how we compared them. So just a quick comment about, I shared that example about how how in the Swiss lab they achieved replacing PID controllers with DRL. The couple of things to keep in mind is that the PIDs are usually tuned by the server administrators, and it has to be done from server to server. It's primarily because each server is different in its own way, like number of GPUs or how many fans are there. Can you control individual fans? Individually you can control it, or can you collectively control it? There are a lot of factors, right? So DRL learns over a period of time from the environment, and it improves on its own. So there's least amount of the expertise involved in running the DRL. So, if you want familiar with DRL, you can check it out. It's a reinforcement learning integrated with the neural network. That's how it works, and it basically self-learns the environment and then improves the efficiency of the balance between temperature and the energy usage. So I do have a little bit of more details, but I'm not going to go through them in the interest of time. So in summary, so BMC is the right place to run the fan control application or the model. So this BMC, this TCU, it's equipped with NPU, which is a neural processing unit. And it doesn't need too much TOPS. TOPS stands for tera operations per second. It doesn't need to be like an LLM, right? So we could achieve this, the power saving, yet we can run the fan smoothly and meet all the needs of thermal control. And then I just want to summarize the benefits. You have cost savings by saving power, and then you are minimizing the CO2 footprint. So there's a formula, so as you might know, PU is mostly for the data center efficiency. There isn't a standardized formula for the server equipments or IT equipment savings. So I happened to chat with some colleagues in Intel, and then when I submitted this, I was suggested to join a forum. I think it's called DCEM. They are trying to standardize the formula. So it's the same thing, but it is more centered towards the power savings on a server basis. So the call for action here, what we suggest is that let's work together, work with OCP, OpenBMC, and DMTF, and try to bring in this ML-based fan speed control. And how can you get involved with this project? The one way you could get involved in this project is that you can pilot this DDML model in your data center. Or we could come up with whatever arrangements you guys are interested in. And we haven't worked out exactly how we want to contribute to the community yet. So by joining the DCM, I believe, the forum, we will figure out, how we can contribute. That's all I have.
Thank you very much.
Thank you.